The PC revolution started this computing world that we live in today. The internet came and connected the PCs together. More recently, mobile has made computing everywhere we go. AI is well poised to revolutionize yet again how we compute, how we connect, and where we do all these things, and make it ubiquitous. My name is Yufeng, and I'm a developer advocate at Google. Today, I want to convince you guys that combining the power of mobile and artificial intelligence and machine learning will make your systems and change the world that we live in today for the better and make for great experiences. Since 2000, half of the Fortune 500 have disappeared. Only a few short years ago, startups and companies would only occasionally mention artificial intelligence as this extra add-on to their business process or to this idea they had. But now, virtually every startup is an AI startup. They just got to tag that on the end, right? Here at Google, we've incorporated AI and machine learning into many of our mobile experiences. And hopefully you recognize some of these on the screen, and hopefully you've found them to be enjoyable. For doing machine learning on mobile, we still train on the server. And classically, we think of training machine learning models as a very compute-intensive action, right? How can we do machine learning on mobile? Mobile devices are lower powered. They can't flex out to many, many virtual machines. So what I want to discuss is the model where we still do the training on the server, but we're going to do the prediction on our device. And you can get away with still using mobile to call out to your server for prediction, and just like a web app or a website. But if you put your actual prediction, put your machine learning model on the physical device itself, it can lead to some amazing user experiences. A great example that I like to call out is Google Translate. It uses onboard machine learning to overlay the translated text. This couldn't be done if it was transferring basically the video of what is being held in front of the screen over the network. Sometimes you might be in another country and you don't have data connection. Furthermore, even if you had data connection, you would want that immersive and responsive experience. Maybe you're on a ship or on a plane where there's no network connectivity. Certainly you don't want to be streaming images over your satellite phone connection. But machine learning, it's kind of hard, right? And making mobile apps, that's no easy feat either. Combine the two, well, that's a real challenge. So how can we make this easier? Today, I want to walk through a particular paradigm that you can use to do custom image classification. So recognizing whatever it is that you want your mobile app to recognize, using a model that will live on the device. So let's take a look at what we're going to build today. So over here, I have my phone. I've got it casting via Chromecast. So if we switch over to the demo, and so what do we have here? This is a camera, basically. And we got some candy here. You might recognize some of these from earlier in the conference. Some of you might have enjoyed some of these peanut butter cups. These are the milk chocolate ones. And over here we have the white chocolate peanut butter cups, and you can see it switching over eventually. And then over here we have some just traditional Reese's peanut butter cups, and you can see that I can move it around, and the confidence at the top is remarkably high. And I've actually got a smaller Reese's cup here, so we got Reese's small and a Reese's large. So that'll switch over. And then just for variety, we got a pack of juicy fruit here, just to, for the people who are allergic to peanuts. And this, of course, all works in airplane mode. So we're in, oh, right, of course it's not going to work in airplane mode in Chromecast. So switching back to the slides, let's talk about how we can build such a system and do it with a way that doesn't involve tedious data collection and labeling and then spending weeks of training on a big server with GPUs and writing distributed code, and then we haven't even talked about how we're going to package that up for mobile, right? As you can see, I used snacks from the conference. I didn't know what snacks they were going to have. I made this week. It took less than an hour, and sure, I did some preparation so that I'd be ready when I got here, but there's no big system running in the background making this happen. So what does it look like to go from training to app? The first step is gathering your training data, and in this case, we're going to do it with video. And sometimes the video doesn't like to cooperate, so I have it, whoops, go back. I have it here. So what I'm doing is literally taking a video of what it is I want to use as training. Because what is a video after all but tons and tons of images being captured really quickly? So if we take this video and split it out into its frames, we end up with lots of training data. And since they're all batched together, one video is one folder full of images to train with. So I just use ffmpeg. It's literally a command line tool. Just copy paste that command line in, replace the file name, and put it in the folder. Name the folder, in this case, Justin's milk chocolate, and make another one for Justin's white chocolate, make one for juicy fruit. And what you get these pictures, right? There's no surprises there. Next step is to upload them to the cloud. We're going to do our training using Cloud Machine Learning Engine and store our pictures in Google Cloud Storage. And that, again, is a solved problem that is basically just running a few commands to upload some files, upload some data, and kick off the training. And then after the training is done, well, we'll get to that. Let's talk more about this training step, right? Don't let me be the one to gloss over the hard work of machine learning. So we're going to do a little sidebar, because it's image recognition, and if you guys have background in machine learning, you know that we're going to use convolutional neural networks. So that's a lot of syllables, and I never won the spelling bee, but it took me a while to understand what a convolution is and what machine learning was doing to recognize images. So I want to use a little analogy of a jigsaw puzzle I recently worked really hard to solve. And this is an MC Escher painting, but it's actually a box cover of a jigsaw puzzle. And usually when you go to solve a jigsaw puzzle, I'm no jigsaw puzzle expert, but maybe you guys have some advanced techniques you can share with me later, but I first separate out the white pieces and everything else. Right? This one was a real pain because the edges there's a lot of white space, and those pieces take forever to put together. So you separate those out and you say, well, I know that the white stuff is like that, and then the rest, well, that's a jumble. That's what a jigsaw puzzle is. But wait, the roofs that are in this painting are a very distinctive pattern. And so I can use that to my advantage. I can go and find the pieces that look like this pattern. And boom, I can piece that together. Then I can say, well, these stairs, they got some of these parallel lines going, and the railings have these X's on the banisters. I can use that to my advantage and find pieces that are of that shape. And then put that together. So what does this have to do with machine learning? A convolutional neural network, in the abstract, can be thought of as looking for these detailed patterns in the same way that your eyes can. It's looking at these sub-patterns and then piecing them together to come to conclusions about the bigger picture. To piece these X's and the lines of the stairs to say, well, there's a staircase there, or there's a roof there. And piecing together the roof and the stair and the hallway and the clock tower, you get the conclusion that you have an M.C. Escher painting. Now, I said there were a lot of white pieces here, and so it took me a really long time to even get to this state. So this is as far as I got, because the other white pieces were just not cooperating. So moving on from that analogy, let's talk about the actual thing I used to train it. And it's using what's called the Inception V3 model. This is a convolutional neural network that Google used to win the ImageNet competition a few years back. And that's a international machine learning image classification competition. And it is 48 layers deep. To give a little context about what 48 layers is and how significantly large that is, as recently as 2011, it was impractical to train a neural network that was more than 4 layers deep. So this was a huge leap. The biggest network the year before this network won ImageNet was 22 layers. So it more than doubled the size and ran through the whole thing and could classify 1,000 different images. And so we're going to repurpose that. We're going to take all of the advancements that were used to make this possible to classify our candy. So what we can do is we take that last layer of the network, and we're just going to train that part. That last step is what separates out into buckets, if you will, the different classes that are being recognized. So in this case, our 5 classes: the 2 different Reese's cups, the milk chocolate, the white chocolate peanut butter cups, and our juicy fruit. So we feed in our input data at the top. You see the Reese's cup at the top. And we make the values in that neural network all the same, and not all the same, all frozen. We don't let it train. We don't let it move. We only let that last layer be trained. So those values get updated during the training, and everything else stays the same. And this step of it, this core piece of it, is a pretty well understood step now, this retraining aspect. And in fact, we have a code lab. I would send you downstairs to do it, but this is the last session, right? But it is online. So you can do this for your own problems as well. And now, moving on from that, I want to focus on what we do to go from a trained model to a trained model on Android. Because if you come at this from the naive approach and say, okay, I got the model, let me put it on Android, it will not work at all. Because the libraries that are used on the Android version of TensorFlow are missing certain operations. Certain operations because you don't want to do training on mobile, as we talked about before. Not much compute power. So we need to strip down the model. And that is nice because the output of this training is 84 megabytes, which is, it's a real whopper. So we want to size that down a little, right? And we're going to optimize it for mobile. So let's talk about this downsizing. There's a command line tool called the graph transform tool. And what it does is it quantizes the model. What is quantization? What it means is that there's the model, which is just a file filled with floating point numbers, decimals. And these floating point numbers are typically 32-bit. So reasonably high precision and reasonably space-taking. So we're going to downsize it. We're going to downsize it to 8 bits. We're going to make all the values 8 bits. But wouldn't that affect the accuracy? A fair question. Thankfully, neural networks are designed to be tolerant of fuzzy inputs. It's designed for a little leniency and still be accurate. So you can get a 4x savings in size with only a marginal falling off in the error, which is great because now we have a 20 megabyte model that we can add to our app. One additional consideration. How we add the model to our app is up to you. You can put the model in the app itself so that when your users download the app from the Play Store, they will have the model built in. And that means your app will be, say, 20 megabytes bigger. So you could also put the model alongside your app as a file. Then when they download the app, they won't have that extra size, but you have other considerations, right? You need to then have logic in your app to download that model on your own at some point. Maybe you only do it over Wi-Fi. What about other advantages and disadvantages? Perhaps you say, well, I really want to keep my model secure. I'm afraid that people are going to look at these floating point numbers in this file and divine some kind of conclusion about it. So I want to keep it secure and packaged in my app. So you might go with the first option. Or maybe you say, I want the flexibility of being able to update my model whenever I want. Maybe just push down the diffs and not update the app itself. So then you say, okay, I'll put the model as a separate file, and then I can have logic in my app to do these updates. So this is a set of trade-offs that you have to weigh for yourself. In my case, I've packaged it with the app, partially because it was more straightforward to just deploy the whole thing to my phone. And so that's what we saw today. We packaged it up, we put it into the app, and that's kind of our full training pipeline, from training to app, or from, in our case, video to app. Turning that video into pictures, training it in the cloud, and then pulling down that trained model and optimizing it for mobile, and then loading it into an Android app. And so you're pretty much ready to ship it. So at this point, I want to step back, zoom out a little bit, and talk about what makes all this possible. Because it's only been in the recent year, let's say, that TensorFlow has existed. Right? It's only been around for, I would say, 15-ish months. And before that, how would you have done machine learning on mobile? How long would that have taken you? Collecting the training data. Where would you have trained it? What would you use to train it? How would you deal with the size of that APK, right? Without having abilities to prune down the size of the model. And you'd have to build your own framework for loading that machine learning model into the device itself. So the reality is what you would probably end up doing is hosting a prediction service in the cloud on your servers and having that mobile device call out to that endpoint with, say, a REST API. And doing that, you incur all the kind of detractions that we kind of talked about earlier, wherein you can't have these immersive experiences, where you can't point a camera at something and instantly have it show what it is. So TensorFlow has really changed the game there. And what's really great is that not only does it work for what I've shown you today with Android, but it is also equivalent on iOS and Raspberry Pi. So you can deploy your mobile app across all of your favorite platforms. Another reason that TensorFlow has been fantastic, both for me and for all of you, is the community. So many people are making examples with TensorFlow, creating really cool use cases, answering each other's questions, and supporting and helping each other grow and build great experiences. And that's only in the most recent year and change. And now that TensorFlow is 1.0 as of mid-February, you can use it with confidence in production, knowing that the API will not change under you until TensorFlow 2.0, which is so far down the road that I haven't even given it a thought until just now. So machine learning on mobile leads to awesome experiences. You can do it now without having to utilize the pains of the past. And the tooling has gotten to a point where you can essentially follow a recipe and have it work. And moreover, to be able to do it for your specific application is what makes it really powerful, because you could certainly load up Inception, that network, with its pre-trained system that can recognize 1,000 different things, but they're just kind of random things, boats and oranges and trees and houses and streets and sidewalks. But you care about specific things, right? You want to build an app that can recognize your things. So being able to retrain it, and being able to retrain it with ease, with capturing video, without having to amass terabytes of data and spend weeks of time to load, process, and train up a model and then still have to make the consideration about mobile, makes this quite awesome. And so feel free to come up at the end. We can play with the app that I made, but that's really a toy example. You saw the way I was capturing that video. I was just kind of walking around, taking the video, trying to do it on a white background because I knew the podium would be white. But in your real case example, real world example, you would perhaps do it with a variety of backgrounds. Maybe in shade and in sunlight. Maybe on white surfaces, on carpet, on wood, on metal. Think about where your users might see the things that you want to recognize. So that's kind of the whole process as a training pipeline. And it allows you to think of it as something that you don't have to have a huge burden on anymore. You can basically pour the data in at the top and then have machine learning in an app coming out the other side. It's no longer a problem where you say, well, let's see, if we're going to make this work, we might need to hire a team of PhDs to think about how we can recognize our specific product. They're very subtle. Some of them are only a little bit different from the others. Inception can take care of that. The model itself notices the most minute differences. And hopefully many, if not all of you, have had a chance to wander a little bit around the third floor during the conference, where we have the example with the candy sorter, which is based on a Japanese farmer who built basically this system, but on a Raspberry Pi, to sort his cucumbers. And I don't know about you, but I can't tell the difference between cucumbers. They all kind of look the same. Even at the store, there's like normal cucumbers, and then they have the fancy ones that are called like European cucumbers, and they're just like longer and thin, but they're all packaged in plastic, so I never know whether or not they're more fresh or less fresh. And in Japan, there's tons of different types of cucumbers, and this guy's growing them all together. And before, he had to categorize these all himself because you sell them to different places, right? And now he has the system that does it for him. And in that situation, you have a very controlled environment. He knows the cucumbers will come down this conveyor belt. He's got the camera, and he will see it in this orientation. In my situation, I knew that I would be pointing my camera at the podium at an angle with a white background under bright lights. So when I trained my model, I found a white table with bright lights and pointed my camera in my video at my objects. I walked around in a circle to cover the angles, but I didn't do much else because I didn't need to. So you can solve kind of a whole range of problems depending on your particular use case. And so thinking through this problem in this model, in this mode, wherein you don't necessarily have to completely start from scratch, but just thinking about a few key points can help with the design consideration, so to speak, and save a lot of trouble down the road. And so I mentioned that there's a way to retrain this or do this online, right? Because the conference is at a close. And so I have a short link for you there. You can do this online. That will guide you through the process of retraining the network, so then you just have something on your computer that does this. And for the mobile side of things, if you go over to tensorflow.org/mobile, it will point you to the Android, the iOS, and the Raspberry Pi GitHub examples that you can literally clone, build, and deploy straight up, no code changes. And then once you have that working, you can connect the two together. You can take the transfer learning, that inception, that first code lab, take the output of that, run the graph transform tool, and then replace the graph that was in your Android assets folder with that one. And then finally, I have the cloud machine learning resource there to learn more about that and how to get that part working, though the code lab at the top does talk about that. So with that, I want to thank you guys.